Assalamualaikum everyone, this is Janatu Sakira Khondokar and today I'm gonna give you a presentation on predicting Alzheimer's disease progression using multimodal deep learning approach. Let's get to know what this paper is all about. As we can see that Alzheimer's disease AD is a progressive neurodegenerative disorder that affects millions of people worldwide. Early detection and intervention are crucial for delaying the onset and severity of AD symptoms. We have basically divided this topic in three different contents. The first content will be summary, the second content will be limitation, and the final content will be synthesis. So in this summary part we are gonna start with the hypothesis. So as we know that this paper is about predicting Alzheimer's disease progression using a multimodal deep learning approach. AD is a progressive neurodegenerative disorder that causes cognitive decline and dementia. Mild cognitive impairment MCI is an intermediate stage between normal aging and AD, and some MCI patients convert to AD over time. The paper aims to develop a method that can identify MCI converters from non-converters using longitudinal and cross-sectional biomarkers from multiple domains. Therefore, there is a need for developing novel and effective methods for predicting AD progression using non-invasive and multimodal biomarkers. So after hypothesis, we are gonna go to the next slide, which is about contributions. So the paper proposes a multi-modal recurrent neural network RNN that can integrate longitudinal cognitive and performance and cerebrospinal fluid biomarkers, as well as cross-sectional neuroimaging and demographic data at baseline. The paper uses a gated recurrent unit to process specifically a gated recurrent unit GRU to integrate the temporal and spatial features from each modality and to classify MCI patients into converters and non-converters. And the paper uses also all available subjects from each modality for training the classifier and evaluates the performance of the method using the Alzheimer's disease neuroimaging initiative cohort, which is in short ADNI. And then we are going to talk about the methodologies here, and there are four methodologies that we are going to talk about. The first one is the paper uses four types of data: demographic information, neuroimaging, phenotypes measured by MRI, cognitive performance, and CSF measurements. And the second methodology is the paper trains a single GRU for each modality separately and then concatenates the four feature vectors produced by each GRU to form an input for the final prediction. The third one is the paper uses 11 regularized logistic regression for the classification between MCI converters and non-converters. And the final methodology is the paper tests the classifier on MCI patients to predict the conversion after 6, 12, 18, and 24 months from the baseline and compares the performance with other methods using cross-sectional or single modal data. And there is a picture that shows us the process of methodology working here. And then we're going to talk about the contribution. The paper shows that the proposed method achieves the best performance with 81% accuracy and 84% sensitivity when incorporating longitudinal multimodal data. And then we are going to talk about the limitations here. There are two limitations that we are going to talk about. The first one is data scarcity and imbalance, and the second one is feature extraction and integration. In the first limitation, the authors acknowledged that their model suffered from the lack of positive samples and the imbalance between positive and negative samples. This could affect the generalizability and robustness of their model. The author also suggested that using more data from other sources or applying data augmentation techniques could alleviate this problem. And the second limitation is that the authors noted that their model could not learn from the final prediction result to update the parameters in each GRU for future extraction. This could limit the ability of their model to capture the features that are relevant to AD progression across multiple modalities. The authors suggested that linking the GRUs to the logistic regression in the second step or modifying the structure of their model to allow for integrative feature extraction could improve their model. And then lastly, we are going to talk about the synthesis. We are going to talk about two syntheses. First one is potential applications and the second one is future scopes. So in potential applications, the author's model could be applied to other neurodegenerative diseases that have similar biomarkers and progression patterns as AD, such as Parkinson's disease of or frontotemporal dementia. The author's model could also be used to monitor the effects of interventions or treatments on MCI patients by tracking the changes in their biomarkers over time. The author's model could also be integrated with other sources of information such as genetic data or lifestyle factors to provide a more comprehensive and personalized assessment of AD risk and prognosis. And the future scopes, the authors could be model could be further improved by incorporating more advanced deep learning techniques such as attention mechanisms or graph neural networks to enhance the feature extraction and integration process. The author's model could also be validated on larger and more diverse datasets, such as those from different countries or ethnicities, to test its scalability and transferability. The author's model could also be extended to predict other outcomes or stages of AD, such as prodromal AD or dementia, or to identify subtypes of clusters of MCI patients based on their biomarker profiles. And that's all from me. Thank you, everyone.